Hello, I'm Qiaomin from Cornell University. Today I'm going to talk about reinforcement learning on Markov Games with Simultaneous-Move. This is joint work with Yudong Chen, Zhaoran Wang, and Zhuoran Yang. We consider two-player zero-sum Markov games with Simultaneous-Move. The game can be described by 5 tuples. S is the state space. For simplicity, we assume that the action space is the same for both players. And P is the transition kernel. R is the reward function for player 1. And in the zero-sum game setting, the reward function for player 2 is exactly minus star. And H is the planning horizon. So in the game setting here, we use the mu and nu to denote the policies for player 1 and 2, respectively. So as step H, as stated as H, player 1 samples an action from the distribution mu H, and the player 2 samples an action from the distribution nu H. And then the player 1 and 2 receives the reward R and minus R respectively. And the system transitions to the next stage according to the transition kernel. We can define the value function for a fixed policy pair in the same way as the Markov decision process setting. So the value function represents the total reward starting from stage S until the end of the episode, if both players are playing actions according to the policy. Now, in the zero-sum game setting, player 1 tries to maximize the value function, and the player 2 tries to minimize the value function. And Nash Equilibrium for the game is a pair of policy, such that each of them is the best response to each other. So for player 1, the policy mu maximizes the value function when player 2 plays the fixed policy nu, and vice versa for player 2. An if-strong Nash equilibrium for the game is the pair of policy, such that the gap between these two best response to value function is upper bounded by if-strong. Here we consider a learning setting for the Markov game. In particular, the Markov game plays the K episode, each week H steps, and at the beginning of each episode, an arbitrary initial stage is given. Then the players play the game according to their policy for H steps, and the game restarts for the next episode and repeats. Here we assume that the transition kernel is unknown. Most players worked on learning Markov games assume that they have access to a sampling oracle, meaning you can obtain the next stage for an arbitrary stage action pair from the oracle here. But in reality, such a sampling oracle might not be available. So players have to learn the systems from the data by playing the games sequentially. This is exactly the setting we consider here. And an important issue we need to address is to balance the trade-off between exploration and exploitation. Our goal here is to find an if-strong Nash equilibrium with as few number of steps as possible. To incorporate the function approximation, we assume that the reward and the transition kernel are linear. So here, phi function is d-dimensional feature vector, and the theta is the d-dimensional unknown coefficients for the reward function. And the beta is the d-dimensional unknown measures on the state space. And under this assumption, the Q function is also linear. So here the Q function is defined in a similar manner as the MDP setting. So it represents the cost to go as stated as after taking actions A and B, and then to follow the policy mu and nu. In particular, the Q function can be written as the inner product between the feature vector and unknown coefficients, the W. I want to point out here, our assumptions of linearity of reward and transition is actually strictly stronger than the linearity of Q function alone. Indeed, the recent work shows some hardness results for a setting with only linears of the Q function. So our linear assumptions here might be essential for developing efficient algorithms. Here is the template of our algorithm. At each episode, the algorithms first updates the policy for both players and then executes the policy to play the game. In particular, in the policy update step, we first estimate the linear coefficients of the Q function by least squares estimation. Now, to encourage its exploration, we used ideal principles of optimism in the face of uncertainty. These principles have been widely used in both Bandit and MDPs. In particular, recalls that the player 1 try to maximize the returns and the player 2 try to minimize the return. So it seems natural to maintain two sets of estimates. In particular, it constructs an upper confidence bound for the best response value function for player 1 and a lower confidence bound for the best response value function for player 2. Now let's zoom into the details of the policy update step. Recall that the player wants the best response Q function satisfies the Bellman equation here and is linear in the feature map. So we can estimate the Q function by estimating the coefficients, the W's from the data. And this can be done by approximately solving the Bellman equation here in using the least squares estimation. Then we can construct an UCB for the Q function by adding an appropriate bonus term. Similarly, we can construct the LCB for the best response to Q function for player 2. Now, given the UCB and LCB for the Q function, the next question is how the players use these estimates to place optimistically to their own goal. Note that the estimates of the coefficients W depends on the value function for the next step. So in order to ensure the estimates here consistently gives the UCB or LCB, we require the value function to be valid UCB and LCB for the Nash value function as well. The key idea of our approach is to coordinate the both players to be jointly graded with respect to the Q estimates. In particular, we can solve a general sum game where player wants the payoff matrix being the UCB and the player 2's payoff matrix being the LCB. Now, if both players play according to the Nash equilibrium of the general sum game, then indeed the resulting value function give us desired UCB and LCB. However, computing Nash equilibriums for a general sum game is computationally intractable. Fortunately, it turns out that there is a relaxed notion of equilibrium named cost-correlated equilibrium. It turns out to be sufficient for our goal here. Recall that a Nash equilibrium is a paired policy that satisfies these two conditions here. So for player 1, policy mu maximizes the expected payoff when player 2 plays the fixed policy nu, and similarly for player 2. The key here is the NE should be in a product form. On the other hand, CCE is the joint policy for both players that satisfies the same condition as the NE. In other words, in a CCE, the players choose the actions in a potentially correlated way, such that no deviation is beneficial. And it turns out that if both players play according to the CCE, the resulting value function also gives us valid UCB and LCB. And more importantly, finding CCE is tractable. For instance, we can solve the CCEs by linear programming. Here comes the complete algorithm. So in each episode, the algorithm first updates the policy. It computes the linear coefficients of the Q function by least square estimation, and then constructs UCB and LCB. Then it solves the CCE for a general sum games with estimate the Q function as the payoff matrix. Then in the policy execution step, both players sample actions according to the joint CCE policy. Now, note that the NE requires the policy belts to be in a product form, So we marginalize the joint policy here to obtain the paired policy for both pairs. Our algorithms achieved the following regress bound. In particular, for player 1, the regress is defined as the summation of the value function difference if player 1 plays the best response policy with respect to player 2's policy. And similarly, we can obtain the same regress bound for player 2. Note that our bound here does not depend on the size of the state or action space. Instead, it only depends on the dimension d of the feature space. To understand the tightness of our bound, recall that our setting actually covers tabular MDP and linear bandits as the special case. So the minimax lower bound indeed provide the lower bound of our setting here. So we can see the square root k dependence is optimal. Now, compared with tabular MDP, our bound is offed by a factor of square root of h, which we can might be able to improve by using a Bernstein styled bonus term. Now, compared with linear banded setting, our bound is offed by a factor of a square root of d. It's unclear whether this extra square root of d can be improved or not. It's indeed an interesting future direction to establish the minimax lower bound for our setting here. It's the standard fact that we can convert the regress bound here into a sample complexity bound. In particular, our algorithms can find an epsilon Nash equilibrium of the game in the number of episodes that scales in this order. In other words, so after k episode, the gap between the best response value function between these two pairs actually scales in the order of the 1 over square root k. As for the proof, here I just want to briefly discuss a key step in our analysis. In particular, we need to show that the value function estimate concentrates along its expectation. Now, recall that in our algorithm, the estimated Q function, value function depends on historical data. And in order to show this, a standard approach is to use a coupling argument to establish a uniform concentration for all value functions. Now, recall in our algorithms, the value function is the CCE values of the general sum games with the Q function as the matrix. It's indeed easiest to cover the Q function. However, this does not lead to a covering for the value function. The main reason is that the CCE value for a general sum game is not Lipschitz with respect to the payoff matrix. So it means if we consider two games with payoff matrix, the green sets and the red sets that are close, then the resulting CCE value might be far away from each other. So it's unclear how to use the covering arguments only in the analysis. Fortunately, the CCE for a general sum game has another property that seems contradictory. So it's say the CCE policy of the general sum game can be close to each other when their corresponding payoff matrix are closed in certain sense. And thanks to this property, then it's sufficient to use the epsilon covering in the algorithm. In particular, given a Q function pair, we can pick an epsilon closed pair from the finite covering, and then compute the CCE of the red pair here, and then obtains the corresponding value function. And turn out that these, if both pairs play according to CCE, then the resulting value function is an approximates the UCB and LCB. And more importantly, we don't need to maintain the epsilon covering in the algorithm. Instead, we can compute the epsilon cover by rounding on the price efficiency. So far, we are mainly focused on the setting. We control both pairs. Our algorithm and the results can be naturally extended to the online setting where only control the one player, while the adversary control the other player. And a similar regress bound can be established. To sum up, we consider reinforcement learning for zero-sum Markov games with simultaneous move. And the key idea of our approach is to use the principle of optimism in the face of uncertainty. And a key subroutine of an algorithm is to solve the CCE of a general sum matrix game, which might be interest over strong. There are some interesting future directions. Due to time constraints, I will stop here. Thanks for listening.